Hello, my Russians. Yeah, welcome. Get some feedback for multiple choice first off. So, question one, we work through packet of EMR, energy 2 EV. Which part of the EM spectrum does the packet lie? So, we just use our E is equal to. Bet you thought it cut out. So, E is equal to HC on lambda. So, therefore, lambda is HC on E. So, we plug in our numbers, we end up with 6.2 times 10 to the minus 7 meters, which is 620, times 10 to the minus 9 meters, which is 620 nanometers. Okay, so you need to know that the visible spectrum is 400 to 700 nanometers or thereabouts. Okay, and below 400 nanometers is the ultraviolet range. Above the 700 nanometers is the infrared range. So this lies within 400 to 700 nanometers. It's therefore part of the visible spectrum. Therefore, our answer is B. Question two. Yeah, no dramas with question two. So we have there, find the centripetal force of the Earth on the Moon. So as long as you recognise here that centripetal force is being provided by gravity, chuck in Newton's law of universal gravitation, you end up with 2 times 10 to the 20 newtons. Okay, easy peasy. Question 3, simple photocell, metal cathode work function of 1.67 eV, light of wavelength 400 nanometers is incident, find the speed of the ejected electron. Okay, so with this one here, we use our regular kind of photoelectric effect equation. So EK is HF minus phi. In this case here, we use F is equal to C on lambda, so it becomes EK is HC on lambda minus phi. Plug in some numbers, make sure that we convert our work function to joules. We end up with the EK is 2.29 10 to the minus 19 joules. Rearrange that, make V the subject, so multiply by 2, divide by the mass of the electron, square root everything, we end up with 7.1 times 10 to the 6 meters per second as our emitted velocity of the electron. Okay, now question 4, a non-ideal transformer, we're told that it's 80% efficient. The power out is 150 watts. That is only 80% of the power input. So it would be fair to say that power out is power in times 0.8, or power in is power out divided by 0.8, which gives us 187.5 watts. That is voltage in the primary times current in the primary. You are told 240 volts is the supply voltage. Therefore, current in the primary, 187.5 divided by 240, 0.78 amps. Our answer for question 4 is B. Question 5. Love question 5. Ask it like every year, 157 times. Here you have a ball thrown at an angle, 45 degrees. As soon as you see that, you need to know it has a Y component, that is a vertical component, and an X component, that is a horizontal component. Okay, now acceleration due to gravity only impacts the Y component, so our X component will always stay the same and will always be non-zero because it's thrown at an angle of 45 degrees. So what we're expecting is it to be nice and symmetrical because it goes up, and what goes up must come down unless it's greater than 11.2 kilometers per second. But this, hopefully, was not thrown by me when I have too much pre-workout, so therefore we are expecting it to come back down to the same height from which it was launched. So our kinetic energy should be nice and symmetrical with a minimum in the middle. If you look at those three graphs, GG, 1 plus 1 plus 1 plus 1 is 4. Nice. Okay, if you look at that, straight away you can get rid of A. Kinetic energy is not going to be maximum at halfway. Kinetic energy should be minimum. It's going to be non-zero. Okay, so therefore we can get rid of C, and kinetic energy can't really be negative because it's half mv squared. M is positive, V squared is positive, therefore it can't be D. Our answer is B. Okay, why is it curvy? Well, think about V is changing at a constant rate because of the constant acceleration due to gravity, but kinetic energy is proportional to V squared. Okay, so therefore it's going to be nice and curvy. Kinetic energy is not changing at a constant rate. Alright, so there we have question 6. Okay, so question 6, what we have here is the aeroplane going down, a magnetic field directed into the page. If you are to use your right hand palm rule, so you've got fingers into the page, our thumb going down the page, therefore the back of my hand should be experiencing a force towards R. Sorry for the mirror imaging. And therefore all of the electrons should go towards R, making R negative, thereby making L positive. So our answer for this one should be C. Electrons move towards wingtip R, so wingtip L becomes positively charged. Alright, now question 7. Biggest thing in question 7 is you're told that the mass and the radius of the Earth are the same. However, this planet X rotates twice as fast. What you need to get from that is that the rotational period changes from 24 hours to 12 hours. Okay, if it's the same radius, it's tracing out the same circumference, it's rotating twice as fast, therefore it must do it in half the time. Okay, so we use our just regular Kepler's third law if you wanted to. Okay, so r cubed on t squared is gm on 4 pi squared. Plug in the numbers. Please do make sure, like, this is by far the most common thing that people forget about. Okay, they forget to square t for whatever reason. Sometimes they'll even write it out, but they'll just forget to plug it in their calculator. They have a little brain fart, and yeah, they lose the mark. Okay, please make sure you don't have any of those brain farts in your exam. Okay, brain farts cost lives. Alright, so r is cube root 6.67 10 to the minus 11 times mass times our period in seconds all squared divided by 4 pi squared. We end up with r is 26645, and then you're like, WTF, there is no answer of 26645 or anything near that. Because when you reread the question, it says altitude, not orbital radius. So we need to subtract the radius of the Earth. And we end up with around about 20,000 Ks. Alright, now in the blue writing, basically what we've done there is we're using proportionality, and you can really only use this if you know what the altitude of a geostationary satellite above the Earth is. Sorry, not altitude, orbital radius. Okay, so I've been teaching this for a while. I remember numbers. Okay, and a number I remember is around about 42297. Okay, so that is the orbital radius of a geostationary satellite above Earth. So, you see in that blue writing, because gm on 4 pi squared is all constant, because the mass of this mysterious planet is the same as Earth, then r cubed is proportional to t squared. Okay, so we are told t is now half. So r cubed should be, proportional to half squared. R cubed should be a quarter. R should therefore be a cube root of a quarter, which is 0.63. So the new value of r should be 0.63 times my orbital radius for geostationary satellite above the Earth, 42297. Chuck it in your calculator. What do you get? 26,645. Okay, or thereabouts. Okay, so it's the same answer irrespective of which way you do it. The only way you can do it using proportionality is if you know the orbital radius for a geostationary satellite above the Earth. Alright, so that's question 7. Question 8. This was just your standard escape velocity question. You're given 3 distracting pieces of information. It's asking for the escape velocity from Neptune, root 2 gm on r. If it's from Neptune, it should be mass of Neptune, radius of Neptune, nothing to do with the sun, nothing to do with distance from the sun. It is legit using these 2 values. And that's it. Okay, your answer should be A, 2.35, 10 to the 4 meters per second. Alright, looking at this graph, hopefully you can see a couple of things in this graph, and focus on the pink one. Okay, so the pink one here, it has a larger amplitude, but you can also see that it has a smaller time. Okay, the time over which this EMF is induced is smaller than the green one, smaller than the blue one, smaller than the red one. So then you got to think. You put your little Faraday's thinking cap on, and you're like, oh my god, what can cause both? We have a larger induced EMF, and it's being induced over a shorter time. I know, speed. Okay, so therefore if they're moving relative to each other at a faster rate, then number 1, it should not take as long, and number 2, you should get a greater induced EMF because rate of change of flux is proportional to induced EMF. Alright, so therefore we get an answer of C. Some of the other options may be able to explain, like perhaps the magnitude change, the amplitude change, but can't explain the time change. Okay, so the relative speed is the only one which can explain both. Alright, question 2 is my standard English brains attempt at a concise question. Okay, so pretty much, there we go, that's better. 2 identical, ideal DC motors, one's 10 volt, one's 20 volt. What is a correct comparison of what occurs at maximum rotational velocity? Answer A, the net EMF for the motor connected to 20 is greater than the net EMF for the motor connected to 10. Sounds good until you realize 2 things. Maximum rotational velocity, what does that mean? That means that it's spinning at a speed, assuming there is no load on the motor, that is, it's spinning at a speed where the back EMF is equal to the supply EMF. Therefore, the net EMF is 0. Same thing for the 10 volt. Okay, 10 volt supply in, it'll keep spinning until it gets 10 volts back, therefore the net EMF is 0. So the net EMF is actually 0 for both motors. Okay, therefore A is incorrect. B, back EMF is not halved for the motor for the 20, it should be double. D, the motor connected to 20 volt supply EMF experiences a greater net force. Well, we say the force on motors is equal to 0, or the net force is equal to 0, because on one side of the coil you have F down, the other side of the coil you have F up. F plus minus F is equal to 0. Therefore, the net force should be 0 on all the motors. Therefore, D is incorrect. C, the current through the coil is the same for both motors. Well, if the net EMF is 0, there's going to be 0 current in both the motors. Therefore, C is correct. All right, now question 11. All right, so I originally marked B as being incorrect because I totes didn't read the question. I just, for some reason, assumed we were looking at side AB because that's pretty much what we always look at in this type of question. All right, so if we're looking at side AB, with our NBIL sine theta, theta shouldn't change. It should say 90 all the time. Therefore, force should be max all the time, which is why I originally said the answer was B. Okay, GG me. Look at side BC. Okay, so BC currently is parallel to the magnetic field, so in our NBIL sine theta be sine of 0, which therefore the force is going to be 0. As it rotates, so you do your right-hand palm rule, you get side CD coming out of the page, side AB going into the page, so it's going to start to rotate, and side BC is going to start to rotate too, and that's going to create an angle with respect to the magnetic field. Okay, so we know that force is proportional to sine of the angle, so therefore we should get a sinusoidally varying graph. Okay, starting from 0 to 90 degrees, where sine theta is maximum, so therefore we should have a plateau at 90 degrees. The answer is therefore C. 12, yeah, no dramas here really, so just make sure you multiply the 57, okay, you're told 57 megatons, the energy in each megaton is blah, so 57 times that is going to give us the total energy. That should be equal to mc squared, so divide through by c squared to get mass, you get 2.65 kgs. Now with question 13. Alright, so some people did put A for question 13 because you found the Y component and you got really happy. Hey, it's pretty close to A, I'll just circle A. You didn't read the question. Okay, it says speed. Speed is resultant. It's not Y component, it's not X component, it is the vector sum of both. Okay, so here when we solve for our Vy, we recognize it says horizontally, so Uy is equal to 0. Therefore we get Vy, plug in some numbers, we get 36 meters per second. Alright, now, looking at the diagram, what you should take away from the diagram is the time that it takes to fall 67 meters is the time that it takes to go horizontally 150 meters. So let's find the time that it takes to become 36 meters per second vertically. Okay, use our acceleration, wrong one. Use our acceleration equation over here. Okay, we get t is equal to 3.7 seconds. So therefore it takes 3.7 seconds to go down 67 meters. And it also takes 3.7 seconds to go 150 meters. So we know the range, we know the time, we can find the x component just by using Sx on t. It becomes 40.5 meters per second, but hey, you guessed it, there's still more. Okay, so here we go. It sounds like the guy from Demtel back, Tim Shaw from Demtel. Oh my god, memories. You guys will have no idea what I'm talking about. Alright, so x component 40.5 meters per second, y component 36 meters per second. Do the vector sum, we end up with 54 meters per second. Sweet. Okay, that could be like a standalone 3-mark question on projectile motion, but cos sigma, we do it as a 1-mark multiple choice question. Sounds good. Alright. Okay, so this is a whole lot of gobbledygook at the moment. I'll just pretend like this never existed. And really, like, we should talk about like what's actually going on here in the transformer. Okay, so if you use your right-hand palm rule, right-hand solenoid rule. Okay, so using our right-hand solenoid rule here for this question, you look at the bottom, a current going into the page underneath, out of the page at the top. You end up with a north pole over here on the right-hand side of the primary coil. That should be a north pole. No dramas. Okay, therefore there's going to be a south pole over here on the left-hand side of the primary coil. So you're going to have field lines coming out. You're going to have field lines coming into the south pole. Now, where are those field lines coming from? Okay, for the south pole in the primary, well, they must be coming from the secondary coil. So here we go. They're magnetically linked, right? Okay, so I think this is what most people did. And then they realized, well, if it's coming from the primary coil, then on the left-hand side, the field lines are coming out. All right, and that's a north pole. So lots of people then said, well, this is going to be north and that is going to be south. But tut. What does a secondary coil respond to? A secondary coil responds to change in flux. So consider what we had before, right? Let's get rid of this for a second. Right now, look at the left-hand side of that secondary coil. How much flux is there going through it? Around about the same number as the number of hairs on my head. That is 0. There is no flux going through the left-hand side of that coil at the moment. Oh, what's going to happen when all of a sudden flux starts to go to the left? Well, what happens, young Padawan, is that secondary coil responds. And it's like, bro, I don't like change, hey. Okay, so therefore, it wants to minimize the change. How does it minimize the change? It gets flux going back into it. Alright, so we've minimized the change. Now we've got flux going into the left-hand side. It'll go on its merry way and it will go through. And we end up with flux going out on the right-hand side. What is that? That is a North Pole, my friend. Okay, so we end up with North Pole down the bottom, North Pole up the top, and everyone is happy. Except the people who got it wrong, which was basically everyone. So no one's happy and that makes me sad. Anyway, 15. Okay, so question 15 actually surprised me how few people got question 15 correct. So again, this is from some past trial paper somewhere. Can't remember exactly, both question 14 and 15 were. Seriously, just consider what happens when, Faraday's iron ring experiment. Okay, so you've got a cell on the primary coil, you've got a galvanometer on the secondary coil. What happens when he switches it on and off? When he switches it on, the galvanometer in the secondary coil deflects in a certain direction, and when he turns it off, the galvanometer in the secondary coil deflects in the opposite direction. Have a look at the options A, B, C, and D. Which one shows deflection or current in I hate saying one direction, but in one direction and then the other direction? The only option is D. Okay, it shows both positive and negative deflection. And that, my friends, is the feedback for your multiple choice. Yeah, yeet!